Lesson 14 is called Intersecting Segments, and it just has a bunch of different theorems about secants and chords and tangents, just kind of all lines that have to do with the circle. So 14.1 is called chords intersecting inside of a circle. So remember that a chord is like a line segment that attaches to either side of the circle and kind of like crosses through the middle, not the middle of the circle, but crosses through the circle and connects to the other side. So like AB in that graphic is a chord, and then so is DE. So the first theorem, if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So if we use this picture as an example, the segments of each chord is referring to each individual little piece. So like from AB, there's this segment from like A to F. So we'll take that length, which is 4. And then the other segment from that chord is from F to B, and that length is 6. We'll do 4 times 6 because it says we take the product of the segments, and product means to multiply. And then that should be equal to the product of the other segments or from the other chord. So from the other chord, DE, one of the segments is from D to F, and that's 3. And then the other segment is from F to E, and that length is 8. So we'll multiply those. So 4 times 6, that's 24. 3 times 8, that's also 24. So it just kind of proves that that theorem is true. And that'll always be the case when you have two chords that are intersecting within the circle. Basically, you can take kind of each individual part from each chord and multiply them together. So like the 4 and the 6. And then that should be equal to the product of the other chords pieces. So 3 times 8. Okay, if you wanted to kind of give yourself a formula for this, of course, the labels and the points can change, but from this graphic, we could say AF times FB or BF equals the product of the other two, or the other chords, kind of two individual segments, so that would be DF. And then times the other half of the chord, which is FE, so times FE. Okay, so AF times FB would equal DF times FE. It's just saying, going back to the theorem really quick, it's the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Okay, so we can use that to find kind of missing values within a circle when we have this situation. So example 1 says, what is the length of segment FE? So you can see segment FE, that's this little part right here, and we obviously don't know it. If you would like, you can just leave it with the label FE, or you can give it a variable if that makes it a little bit easier to kind of understand. I'm going to label it X. I just like to label my unknowns X a lot, so I'm going to use that. So we know that if we take one chord and we take the individual segments from it and multiply them together, it should be equal to the individual segments multiplied together of the other chord. So from this chord right here, DE, the individual segments, one would be 30 and the other would be X. So I would say 30 times X equals, and I would set that equal to the other chord. So the other chord, the individual segments are 45 and 2. So I would say equals 45 times 2. And then now I have an equation with one unknown, so I can solve for it. So I'll leave the 30x alone for right now. And then 45 times 2 is 90. And then my goal is to solve for x so that I can find that length of FE, because that's just what I labeled x as. And then from there, if I want to get x by itself, I'm going to divide both sides by 30 to cancel out the 30 that's being multiplied by x. So 30 divided by 30 cancels out, and it leaves me with just x equals 90 divided by 30, which is 3. And then since it asks specifically what is the length of FE, I'm just going to write my final answer as segment FE equals 3. And when I say you can label it as X or you can just leave it as FE, what I mean by that is like when you wrote your original equation, if you wanted to just do like 30 times FE instead and leave that as your kind of like variable, you could also do that if it helps make it more make more sense. That was weird. Okay, so example 2, what is the length of RT? So if we look at our graphic, RT is like this entire chord right here. You'll notice that there's already some unknowns in there. We have like all the different segments labeled, but some of them have X's. So what that means is we just kind of have to figure out like what is the value of X by setting up an equation, and then we can kind of backtrack and fill in to figure out what that whole chord's length is. So we'll take the individual pieces of each chord and set them equal to each other. So one part of the chord RT is 8, and then the other part is x plus 5. So since I'm multiplying 8 by x plus 5, I need to put x plus 5 in parentheses, and we will have to distribute or else you won't end up with like the correct length for that chord. And then that's going to be equal to the other chord, which should be its 2 parts, 4x, and then times 12. So we'll do 4x times 12. And then now we have an equation that we'll be able to solve for x, and then ultimately we'll be able to put that x back in to find the length of RT. So on the left side of the equation, I'm going to have to distribute. So I would do like 8 times x, so 8x, and then 8 times 5 is 40. And then over here I can multiply the 4x times 12. You just need to multiply the 4 and the 12 to get 48x. And then now you notice like I have one term with an x on the left side of the equal sign and one on the right. Usually when that's the case, now we want to kind of get them on the same side. So I'm going to go ahead and cancel out that 8x on the left side just so I don't have to deal with any negatives. So I'll subtract 8x right there to cancel it out. And whatever I do to the left side of the equal sign, I need to do to the right as well. So we'll do minus 8x right there. I'll bring down my 40. And then 48x minus 8x, I just have to subtract the coefficients, the numbers in front, so it would be 40x. And then my ultimate goal is to get x by itself, so that 40 is being multiplied by x. I'm going to divide both sides by 40 to isolate x. So 40 divided by 40 is 1, and then over here the 40 divided by 40, that would be 1x, or they would like kind of cancel each other out and just leave us with x. So we end up with x equals 1 as my like length of, or my value of x. And then the original question was, what is the length of RT? So you'll notice like RT is x plus 5 plus 8. So I'm gonna just write that out. Segment RT is x plus 5 from that like first part from R to F, and then plus 8 from F to T. And then now I just need to take that 1 and substitute it in for x, and then that'll give me the total length of segment RT. So it'd be 1 plus 5 plus 8, and then 1 plus 5 is 6, and then 6 plus 8 is 14. So the length of segment RT is going to be 14 units. Moving on to 14.2, the title is Secant Segments Intersecting Outside a Circle, which sounds like a tongue twister to me. But a secant segment or a secant line of a circle is a line that intersects the circle at 2 points. So the theorem, if 2 secant lines intersect in the exterior of the circle, so you can see that on the graphic, between A to E and G to A, then the product of the lengths of one secant segment and its external segment is equal to the product of the lengths of the other secant segment and its external segment. So I know it feels like a lot, but we'll kind of use the picture to pull that all together and make a little bit more sense of it. So this one is quite a bit different than 14.1 in that you don't just get to multiply the 2 individual parts like 4 times 14 or 3 times 21. So right here where it's saying the product of the length of one secant segment, so one secant segment is this entire thing, like all the way from A to E, and its external segment, that's just the part that's outside of the circle, so that part is just a to b. But it feels like we should just be able to like multiply the two individual pieces because that's what we did in 14.1, but it's just a different theorem. So we just have to be a little bit more careful with that. So for this one, if I'm trying to find like the entire length of that secant segment, I would have to add 4 plus 14 because the first part is 4, the second part is 14. So 4 plus 14, that entire length would be 18. So now if I'm going to multiply the secant segment by its external part, I would do 18 times 4, and then that would be equal to the product of kind of like the same situation for the other segment. So on the other side, like this is the entire secant segment. So from 3 to 21, or not from 3 to 21, but from A to G and like the lengths of 3 and 21. So we'd have to add them together. 3 plus 21 would give us 24. And then we would multiply that by just the external part. So just A times, or A to D, so it would be just 3. So we would do equals 24 times 3. So it would be 18 times 4 is 72. And then 24 times 3 is also 72. So their products are equal, and that'll be always the case when we have this situation. It's just really important to remember, like kind of comparing between the two theorems. In the first section, like in 14.1, we had chords that were like just strictly inside the circle, and that's when we're able to just multiply like kind of each half or each portion of it. Versus in 14.2, we have secants, and these segments extend out past the circle, like to the external part. And when that's the case, we're going to have to find the length of the entire segment. So like adding the 14 and the 4, or adding the 3 and the 21 to find the length of the entire segment before multiplying it just by its external part. Okay, so example 1, what is the length of segment IV? So we'll be able to set up an equation here. Same thing as kind of before. If you would like to label segment IV with a variable, if that helps you set up your equation, you can. That's what I'm going to do. I'm going to call it X. So we know that with this theorem, we have to find the total length of the secant segment. So for BV, it's going to be not just 5, but 5 plus X. So I'm going to do X plus 5. And then that entire segment, X plus 5, is going to get multiplied by just the external part. So just the external part of that is the 5. And since I'm multiplying the 5 by like multiple terms, I'll need to put that X plus 5 in parentheses. So anytime you're multiplying a number by multiple terms, and when I say multiple terms, like this is one term and then there's addition sign, so this is another term, you would need to put them in parentheses. So this is the external part, the 5, the part that's highlighted in just green, and then multiplied by the entire segment from B to V, like the whole part that crosses into the circle. And then that should be equal to the product on the other side. So on the other side, I'm going to just start with the external part. So the external part is 3, so equals 3. And then it's going to be multiplied by the entire segment, which is 3 plus 22. So 3 plus 22 is 25. So the entire segment is 25. So 3 from the external segment, that was just this part right here. And then 25 from the whole segment, 22 plus 3. And then from there, we're going to go ahead and distribute the 5 into the parentheses. So it would be 5 times X, and then 5 times 5, so plus 25. And then over there on the other side, 3 times 25 is 75. And then now I just have the X on the one side of the equation, so my goal is to just get it by itself. So I'll need to cancel out that 25 that's being added to it, so I would subtract 25 from both sides. Bring down my 5X, 25 minus 25 cancels out. 75 minus 25 is going to be 50. And then still trying to get x isolated, so now I have a 5 that's being multiplied by it, so I'll divide both sides by 5. 5 divided by 5 cancels out, so I'm left with just x, and then 50 divided by 5 is 10. So I have x equals 10, but this problem was asking for what is the length of IV. So the length of IV is like, oh wait, no, hold on. I was thinking we had to go BV. That's cool. Okay, so we're done pretty much. Okay, we're just gonna write our final answer. I was thinking it asks us for the length of the entire segment, but it just asks us for IV, which is that portion that we labeled with X. So I'm just gonna write my final answer as segment IV is 10. Okay, if for whatever reason they did ask for, like, say, what is the segment length of segment BV, you would approach it the same exact way. You would just have one additional step at the end of like adding your, like, what we found for X to the 5 to finish it out. Moving on to example 2, it says, what is the length of segment PD? So segment PD is right here. I'm going to go ahead and just continue to label like our unknown, what we're looking for, as X. And then we're going to set up an equation where we're multiplying the external part by like the length of the full secant segment. So I'm going to start with the side that has X in it. So my external part is just segment PD, so it's just X. And then for my like whole entire segment, it's from C to P, and they give us the whole distance this time. So like on a previous problem over here, like on the left one, we were just given this part. So we had to add like X plus 5 to get the entire segment. But on example 2, we're given like the whole length from C to P, and that's 20. So that means that like this entire distance is 20. So I'm going to just say X times 20. And then that's going to be equal to the product of the pieces on the other segment. So the external part is 10. Times the entire segment is going to be 10 plus 8, so it'd be 18 for the whole segment. So 10 times 18. And then one more time the setup, we took X, the external part from the segment on the right, we multiplied it by the entire length, which was 20, and then we set that equal to the external part on the left side, 10, times the entire length of the segment, which was 10 plus 8, so altogether 18. And then we can multiply 20 times X to get 20X and 10 times 18 to get 180. And our goal here is to get X by itself. So I need to cancel out that 20 that's being multiplied. So I'll divide both sides by 20. And then 20 divided by 20 cancels out. And it would leave me with just X. And then 180 divided by 20. Kind of like a trick whenever you're dividing by like something that both has zeros, the like 1 0 will cancel out 1 on the denominator. So now I can really just do like 18 divided by 2. So I end up with X equals 9. And X was what I labeled segment PD. And this question is asking for what is the length of segment PD. So we'll just say PD, or segment PD, is 9. Moving down to 14.3, this one is called tangent and secant segments intersecting outside a circle. So somehow it's even more of a tongue twister than 14.2. But this theorem says if a secant line and a tangent line, I'm going to pause there. So a secant line is a line that intersects a circle in 2 points, and a tangent line is a line that intersects a circle at 1 point. So if a secant line and a tangent line intersect in the exterior of a circle, then the square of the length of the tangent segment is equal to the product of the lengths of the secant segment and its external part. I know it feels like a lot. I wrote like a formula version of what that's saying. So the tangent segment is AD and the secant segment is AE. So what this theorem is stating is if we take AD, the tangent segment, and we square it, that's going to be equal to the product of the secant segment, AE, and its external part, so AE and its external part, which is just a to b. So example 1, I'm going to leave it zoomed out just so we can kind of see this picture as a reference. But example 1 says segment ED is tangent to circle A. What is the length of ED? So we're trying to find the length of ED right here. I'm going to go ahead and label it as X. And then since that is the tangent segment to the circle, that's the part that gets squared. So I'm going to add a little note in here that like this is coming from the line that's tangent. And that means it only touches the circle at one point. And the other two parts are from the secant segment, because the secant segment can have two parts. It can have like kind of the external part and then the entire thing that crosses through the circle as well. So for example 1, since we're trying to find the length of that tangent segment, that's the portion that gets squared in our equation. So when we set up our equation, it would be x squared equals, and then we're supposed to set it equal to the product of the length of the entire secant segment. So the entire secant segment is 7 plus 9, so that would be 16. So equals 16. And then times just the external part. So just the external part of that segment is the 9, so we do 16 times 9. So the x squared came from the tangent segment that we don't know, and the tangent segment is the part that gets squared. And then the 16 is the entire length of the secant segment, so 7 and 9 together, and then 9 is coming from just the external part. We don't have to include just the internal part. Okay, and then x squared equals 16 times 9 is 144. And then we're trying to get x by itself, so I would need to square root both sides to cancel out the exponent. And then that would leave me with x equals, technically the square root of 144 is positive or negative 12, but we're talking about the length of a segment here, so we would just need to include the positive version of it, so just positive 12, and that x we use to represent segment ED, so I'll say segment ED equals 12. And then example 2, segment ED is tangent to circle A. What is the value of x? So this one I am going to zoom in on. So this one, we have pretty much everything labeled, but we just don't really know what x is yet, so we don't actually know the length of like C to F, for example. And we just want to find the value of x, so we need to set up an equation using like this formula up here. I'll try to fit it. Okay, so that formula tells us we have to take the tangent segment, which is the one that just hits the circle at one point, and we square it. So that would be 6 squared. And then we set that equal to the entire length of the secant segment. So the entire length is like all the way from D to C. So from D to C, it would be 2x plus 1. That's the first part. And then plus 4. And then I can go ahead and I can combine the 1 and the 4, add 1 and 4 to get 5. Just to get like a simplified version of that. And then I'm going to take that 2x plus 5. I'm going to have to multiply it by something else. So I'm going to put it in parentheses. And then the next part that I multiply in is the external part of the segment. So the external part of the secant segment is just that 4. So I'm going to multiply that 4. It does not matter if you put it in front here, or sorry, behind there or in front, you will just still distribute the 4. It's kind of nice to be comfortable both ways. So the 4 can go in front of the parentheses or behind. Either way, we're going to multiply them together and distribute that 4 in. So 2x plus 5, that was from the entire segment. 4 was just the external part. One more time, it became 2x plus 5 because we did 2x plus 1 plus another 4, and then 1 plus 4 became 5. So I'm going to square the 6, that'll be 36. And then I'm going to kind of like distribute the 4 backwards. So we'll do 4 times 2x is 8x, and then 4 times 5 is 20, so plus 20. And then I just have the one term that has x now, so that means I want to like start to isolate it. So I want to cancel out the things that are being done to that x. So I'm going to cancel out the plus 20 by subtracting 20 from both sides. So 36 minus 20 is 16. And then we bring down the 8x, and then 20 minus 20 cancels out. Now I just have an 8 that is being multiplied by the x, so I'm going to divide both sides by 8. And then 16 divided by 8 is 2. So I end up with x equals 2 for my final value of x. And this problem was just asking for what x was, or what is the value of x, so we're done and we can stop there.